And we're live! Welcome to our Facebook Live for RockSim. My name is Tim Van Milligan. Today we're going to talk about Optimum Mass. Now, Optimum Mass is a weird topic. It's a very high-end, high-level topic, so I don't want to get anybody confused. But before we do that, I got some house cleaning things to do. First, this is Facebook Live. My name is Tim Van Milligan. From last time, this is our second episode, and it's going to be about an hour long. And I'm looking for my list. But about an hour long, and the purpose of these videos is for RockSim training. We're here to answer your questions. I don't need to answer my questions because I already know about it. So you are important. So if you have questions, you can type them into the comments field on Facebook. If you're watching this video afterwards as a replay, what I'd ask you to do is not put them on Facebook, but to send them to us via email. And if you come to the Apogee website, you will find our contact form and just email them. And that way we have a better record of them. We don't have to go onto Facebook to find what people want to hear about. So this is for you. So if you have questions, be sure to ask them. Now, in this particular episode, we're going to talk about Optimum Mass. And it's a pretty long topic, so I'm not sure if we're going to get to other questions. And in fact, we have another question from last time that I want, if there's time, I'll answer. Let's see, let me see who it was that sent it in. It was Tom Lacook. He asked about adding a 3-motor cluster. So if we don't get to clusters, Tom, we'll do it next time. The question that we're answering this time came from Steve Crystal. Steve Crystal is a competitor. He flies rockets in competition, and he is on the international team representing the United States. And the international team is supposed to go to Romania this summer to compete against other countries. So it's who can fly the highest, who can keep their rocket in the air the longest, things like that. And his topic is Optimum Mass because he wants to fly his rocket the highest. So this is RockSim, and let me go here and share my screen. And as you can see here, on the Apogee website, I can show you where to find RockSim. Here in the scrolling banners, if you click on the scrolling banners, you'll find the one that says RockSim, and you can just click on that, and that will take you to our RockSim page where you can order it. You can also download the free trial version. So if you download the free trial version, you have 30 days to experiment using RockSim, and then after that, then you need to decide whether or not it's something that you want to commit to. If you want to send us an email while I got this up, over here on the side, we have where it says talk, and then you go down here to the contact form. You click on that link, contact form, and there you can send us an email. So if you see that, if you have something to ask, that's where you would go to send us an email. Today, what we're going to be talking about is Optimum Mass, and for that, the information about that, I don't have a previous video on Optimum Mass. So what I do have are newsletter articles. There's 2 newsletter articles that you can read, and they're free. To find them on our website, go to our menu bar here at the top, and you click on the how-to and guides, and that will bring up this page or this choice right here, and then go here to Peak of Flight newsletter. and then go all the way over here to all newsletters. And you click on that, and this will give you a list in chronological order of all letters. And the two newsletters that talk about Optimum Mass are number 84, so you got to go way down to the bottom because we have over 500 newsletters. So 84 is Optimum Mass versus peak delay time. And we've taken peak delay time mass out of RockSim. So that won't have to cause any confusion, but the Optimum Mass starts there. And then issue number 200, you'll want to see where it says tips on finding optimum mass. Now this is the advanced one, which is what I'm going to be covering today. So first of all, what is optimum mass? And let me switch screens here so you can see my face. All right. We don't need that anymore. Okay, so I'm back here behind this computer. Now, last time I had my laptop here, and my laptop had some problems, and right now it's in the shop. So we brought in a big monitor computer, an iMac, and this will do everything that my other computer did, but it's just bigger, and it takes up screen, and you can't see the nice poster back here that says the first step into space is an Apogee model rocket. Yeah, this monitor is in the way. You can't see that. I don't want to touch the monitor. So that's kind of why I've got a big monitor here. But what I want to talk about is optimum mass. So imagine you are holding two small balls. Now one ball is a ping pong ball, and the other ball is a golf ball. Now you're going to tee these up and hit them with a golf club. Now you tee up the golf ball. Now you can say, I'm sure you can find these plastic golf balls, if you want to compare apples to apples. So they're both exactly the same size. One's made of plastic and it has the dimples in it and everything, and the other is a real golf ball. You tee up the plastic ball and you hit it, and it probably goes 50 feet. As hard as you hit it, it goes 50 feet. Then you tee up the real golf ball and you hit it, and you can drive it, 200 yards. Now, think about this. One is lightweight and one is heavy. Why does the heavier ball go further than the light ball? And this is where it gets into optimum mass, and because it really comes as momentum. But now you have those two balls, and then you tee up on a third ball. Now this third ball is made of cast iron, and you set it up there and you tee it off, and this one only goes 30 feet. So you had one ball, the ping pong ball that went 20 feet, and then you had the golf ball that went 200 yards, and then you had the heavy iron ball, and it only went 50 yards. And so what you come across here is that in this situation, there's an optimum mass. And if you can if the golf ball had the optimum mass, you could hit it the furthest. This is the same principle in rocketry. In rocketry, we want the rocket to go as high as possible. So obviously we want it light, but can you make it too light? And that's what optimum mass is all about, and what RockSim can help us find. Okay, so let me go here to my RockSim screen, and let me just bring up RockSim, and hopefully we got the entire screen here. I'm going to open up an existing design. So I'm just waiting for it to open up. We've got this computer really thinking. It's thinking so hard, it's taking a long time. We're trying to do broadcasting, simulcasting, plus we're also doing recording of this video so that we can replay it later. And say OK. All right, access to desktop folder, OK. So now I got to go to my applications folder, because that's where my RockSim folders are stored. So I'm going down here to RockSim, and it's in the design folder, and I'm going to open up the Apogee folder, and then I want to find, I got all kinds of images in here. Yours is, when you first open up RockSim, you're not going to have all that stuff because we've been playing with this particular one. And I want to open up the one called the Spec NAR Altitude Rocket. And open that up. I'm going to skip that. So as it opens up, we see the rocket on the screen. And let me go back here. Okay, so this is the spec rocket that I'm just opening up, and I'm going to use this as an example because this is a rocket that I designed to be an altitude rocket, and I want this rocket to go as high as possible. And it's pretty small, as you can see. It's a two-stage, and we'll talk about two-stage rockets a little bit later. It takes a 13mm diameter motor, and it's got this big area up here. And you're wondering, why would I have a big area up here? And the reason is we have to put an altimeter in this rocket to measure how high it goes. And I designed this rocket around a altimeter that will fit into an 18mm diameter tube. We have multiple altimeters. We have two small ones. One is the Micro Peak from Altus Metrum, and that's the one that will fit in here. Perfect Flight used to have one called the Firefly, but Perfect Flight hasn't been shipping us altimeters anymore, but that would fit in here if you had an old one of those. We also sell one called the Adrel. It is really, really tiny. This one will fit into a tube that's 10.5 millimeters. So that's smaller than the rear diameter here. And if I take this altimeter, and I don't know if you can see this or not, but it will actually fit in there really easy. And here's the battery for it. The battery is equally as small, and you can see that battery will also fuse. So this altimeter would actually fit into this rocket. If I had a nose cone on it that was 13mm, but I designed the rocket for 18mm altimeters, so that's why it has the big bulbous nose on it. Anyway, so once you're in RockSim, we need to run a simulation to start this process of finding optimum mass. So I'm going to go here to simulations, and I'm going to see if there's any simulations that have already been run. I better turn on my screen share so you can see it. So I'm in RockSim, and I clicked on the Flight Simulations tab right here on the top. And we have an A10 or an A3 motor. I'm going to click on the A3 4T motor. And then I'm going to go up here at the very top of the screen on the menu bar. There's, under the simulation menu, there's a feature called Predict Optimal Mass. And if I click that, it just quickly reran the simulation and brought up this optimum mass screen. Now, what I'm going to show you, the first time I run this, I'm not going to get the optimal mass. So the first time you click on it, be prepared that this is wrong. Because we haven't really set up the situation properly. But I want to go through it first because I think this is the reason why this question came up. Because Steve Crystal, when he went to RockSim and he went to the optimal mass screen, the results didn't make sense. And it's because we didn't set it up properly. And I'll go through the proper way to set it up, but I want to show you what happens if it's not set up properly. So if we're here on the optimum mass prediction screen, and we just click the button that says start the simulations, and what RockSim is doing is it's running a number of simulations to kind of find the optimal mass. You can see we're well over 200 at this point, and I'm going to stop it because it's taking way too long. It should do this really quick. So that's the first thing you want to do. Is now we're going to start setting things up properly. So I'm going to click the button that says automatically calculate the optimum mass, and I'm going to click the button that says generate graph data, because that's what I really want to see, is not too light, not too heavy, but somewhere in between. So I want to see a curve of mass versus altitude to see where it peaks. What is that peak point, that optimum point for altitude? So I'm going to click generate that graph data, and now I'm going to restart the simulations. You can see it's doing them again, but this time it only did about 20 simulations instead of over 200, and he didn't get to the results back then. So it's telling us our current sustainer mass. So here on the bottom, this is our sustainer, the first set of fins. So if you pull off the bottom, this is a booster, this is your sustainer, which is the top part of the rocket. Our sustainer, RockSim is telling us it weighs 12.216 grams. And down below here it says our optimal mass, what it currently thinks it is at 4.2 grams. And if we put the rocket with this motor, and if it weighed 4.236 grams, we should reach an altitude of 834 feet. So this time I brought my scale with me, and I can actually weigh the rocket. So you can't see the numbers on the screen, but I'll tell you what they are. Right now, this rocket weighs 8.5 grams. So according to RockSim, I'm way too heavy. So no matter what I do, if that optimum mass is correct, I'm way over my optimum mass. But let's look at the chart. So if I click plot graph, ooh, actually I got a really good chart here. I got a nice smooth curve. A lot of times when you open up this chart, you don't get this nice smooth curve. It will be jagged, and there's a reason for that, and that's because of the setup. But if you have a nice smooth curve like this, that tells me that most of the way it's set up. And this curve, this particular chart of mass versus altitude has a name, and it's named after the person that first created one of these charts, and his name was Douglas Malwicki. So we call these the Malwicki charts. So for this rocket, the spec rocket on an A3-4, here's our optimal mass, and you can see if we're below the optimum mass, we're going to get a lower altitude, and if we're above the optimum mass, we're going to get a lower altitude. It's only when we're at that optimum mass do we get the actual altitude. Okay, so that's that. It seems simple so far, right? So let's cancel out of this, and let's rerun a simulation. So I'm going to choose a motor, and I'm going to choose that Estes A3-4T. So it show all motors, and only those that match the engine mount diameter. And here's the Estes A3, and we're going to choose the 4-second delay, and click OK. Now it's showing here that the engine is loaded in the back of the sustainer. This is our booster. We're not loading anything in the booster. When you run RockSim, you don't have to load motors into all the stages if you don't want, and that's what we're going to do. We're going to ignore the booster for right now. Then we're going to go under flight events. I'm going to expand this column so you can see what it says here. And it says deploy the streamer at maximum engine ejection delay. So it gets to 4 seconds after engine burnout. It's always measured from engine burnout, not from when you launch the button. So 4 seconds after engine burnout, the rocket's going to separate, and the streamer, if there was a streamer in this one, would come out, and then the rocket would start descending down to the ground. Now we're going to look at, I want to look at the starting state, because I wanted to see how this was set up in the past, because this is not my personal computer, so I didn't know how The person that used this computer had set up this simulation before in the past. So right away, I see the launch guide length at 72 inches. That's 6 feet tall. Now, normally when you fly a rocket that's this small, you're not going to be on a 72-inch launch rail. It's usually going to be 36 inches. So I want to back that down to 36 inches because you want to make this realistic so that you get realistic results. Our launch angle is straight up, and that's good because when we launch, we always want to launch straight up. And then under our launch conditions, so here is our simulation, and first of all, I want to turn cloud coverage off. So that means no thermals, because what can happen is if the streamer comes out and the rocket is descending, and what happens when the rocket descends is, on a real day, you get what's called a thermal. A thermal is a rising column of warm air. Now, warm air is lighter than cold air, so warm air rises like a hot air balloon. And sometimes your rocket, as it's coming down on a parachute or a streamer, can get caught into one of these thermals, and it can actually carry the rocket back up in the sky. And this happens all the time, particularly for really lightweight rockets like this. So I want to prevent that from happening, because if the rocket goes back up in the sky, I can exceed that 800 feet that RockSim said that this rocket could go to. So if I get 1,000 feet and then I say, hey, what's going on here? Why is the rocket going higher than it predict? And it's because, it could have gone up, started coming back down, and then gone back up again. And then now I got a new peak altitude here. So I want to avoid that situation. So I say, let's turn off the sun so that the sun is not heating up the ground, heating up the air, and causing the air to start rising again. So I always run my simulations with the thermals turned off. So no thermals. So this whole column here on the right side is ignored by RockSim when it does its simulations. Over here on the other side, this is our other conditions. We're at an altitude of 700 feet. This is kind of like in the Midwestern part of the United States, and that's fine. Temperature, this is a standard atmosphere day. So 59 degrees is not dead of winter. It's not the middle of summer. It's kind of, spring or fall. So it's kind of an average day, and that's why it's called an average day. The barometric pressure, I'm not going to worry about. But I do have wind, and right now it's telling me I have a light wind, and it's 3 to 7 miles an hour. But I don't know exactly where it is, because what RockSim is trying to do is to create a realistic day. Because when you go out to the launch field, realistically, it might be a light wind, but you don't know how light it is. A 3 miles per hour wind, or it could be 7 miles per hour, or it could be somewhere in between. And this creates pretty realistic simulations. But for predicting optimal mass, it really can screw things up. So when I was showing you before, getting that nice smooth curve, that nice smooth Milwaukee chart, this right here is the first thing that can screw it up. Because every time we launch the rocket, we could get a different altitude. So let me go ahead and just run a simulation here real quick and show you. So I click launch, and it's running a simulation, and right now I get 736 altitude. If I just click the launch button a second time, it's going to rerun the exact same simulation. Nothing's changed, but I got a different altitude. Why is that altitude different? And the reason is because the wind was different. RockSim uses a random generator for predicting the wind speed. So the difference between these two flights is the wind changed. So if you keep clicking that launch button, and I'll just do it again, show you again, we got a different result. So how can you predict the optimal mass if the wind keeps changing your altitudes? And that's why you can get these really jagged charts for the Milwaukee plot. So we need to turn that off right now. So I'm going to go back up here to prepare for launch, go over here to launch conditions, and now I can run it with wind, or I can run it without wind. The choice is yours, But when you run it with wind, it has to be a constant wind. And if you want to set up a constant wind under wind conditions, pick custom speed range. So now we're going to have a custom speed range, and you want to set the low wind speed and the high wind speed to the exact same value. So I'm going to choose 8 miles an hour for the low and 8 miles an hour for the high. So now RockSim is going to have a random number generator, and it's going to pick a number between 8 and 8. There's any number between 8 and 8. You see what I'm getting at? It's going to be 8. No matter what, it's going to be 8. No matter what this wind turbulence says. So if I pick constant speed or any one of the custom turbulences, it's always going to be the same number. So let me go ahead and launch again just to show you. So the first time we launch with 8 mile an hour wind, we get 728.73 miles per hour. If I hit launch a second time, I should get exactly the same number. So now we're getting consistent results. Okay, so now I want to go back to the simulation and predict optimal mass. And I want to do it again. Start the simulations. It reruns the simulations. And now look at what happened. Remember the first time, I think it was 4.7 miles, 4.7 grams. Now we're at 8.222 grams that it says. So remember, when I weighed my rocket, and I'm putting it on the scale again, I'm at 8.5, but I'm still over optimum mass, but I'm not too far off. Look at the plot this time. Oh, okay, now this is what I wanted to show you the first time. This does not look like that first chart, right? That first time we looked at it, it was nice and smooth, and it had a definite peak at the very top. Here, I got a flat line, it spikes up, and it's almost a curve, but it's not quite a curve. It looks a little bit jagged over in this area here. Now this is the second part that we have to worry about. What I want to get is that nice smooth curve. So how am I going to do that? So first let me cancel out of that and kind of explain what is going on here. Let me switch so you can see me. Okay, here I am. When we launch our rocket, there are a number of variables that are acting. One of them is mass, which is the one that we're trying to isolate. The other variable is the location of that mass on the rocket. And then there's another variable that we have to worry about, and that is our coefficient of drag. The coefficient of drag is the one that plays the biggest role. When we launch this rocket, we need to know what that coefficient of drag is. RockSim is trying to estimate it, and it does a pretty good job, but it's not perfect. But and the reason is that coefficient of drag is not a static number. Let me say that again. Coefficient of drag is not a static number. So this rocket is going to have a couple of, well, actually it's a whole spectrum of coefficient of drags. And what it depends on is two things. The first one is the speed of the rocket. So the faster the rocket goes, the higher the coefficient of drag. The second one is the angle of attack. So if the rocket is going straight up, its coefficient of drag is different from if the rocket is kind of crabbing its way up into the sky. So what we need to do when we're running optimum mass calculations is to fix that coefficient of drag at a specific number so that it's not varying throughout the flight. On RockSim, let me go to my screen view here. So I'm going to go, where's my cursor? Here's my cursor. I'm I'm going to click on this simulation, the last one that we ran, and I'm going to go here to the plot screen. I'm going to plot a graph. This time I want to plot speed. So we're going to have, let's see, we want speed, it doesn't really matter. We're going to have coefficient of drag and on one axis and speed on the other axis. And I'm looking for velocity. Altitude, drag, flight angle, wind angle of attack. Oh, here's my velocity. Velocity. And I'm going to plot this graph. And you can see, let me expand this so I can make this bigger for you. So down here on the bottom we have velocity, and at the top we have coefficient of drag. And as you can see, what we're actually seeing is two velocities being overlaid on top of each other. And you can say, why is there two velocities? Well, one is the rocket accelerating to its peak speed as it's taking off, and the other one is decelerating. So then it starts slowing down again. So you have speed going up, speed going down as the rocket's coasting upwards. And so that's why we're getting this kind of this double line right here. I'm going to choose probably this smoother one here to kind of show you. That's probably the one where the rocket is slowing down, because on the way up, other things are changing, like the mass of the rocket is changing as the rocket is burning off propellant. So you can get some weird spikes going on. So I'm looking at this, and you'll see, the thing that I want to point out is that the coefficient of drag is changing throughout the flight. And this is going to screw up your optimum mass calculations. So we need to create a situation where the coefficient of drag is just a straight line. It'll actually be a vertical line if we plot it like this, no matter what the speed is. Or it's going to, yeah, or actually it's going to be a horizontal line. It could be like 0.6, no matter what speed the rocket achieves. And we need to set that up. And to do that, I'm going to go here to this tab called CD Override. But at first, I need to have a CD to start with. So let me go back to that chart, same chart. And I'm just going to pick a number off this chart. And it doesn't matter which number. So I'll say at 100 miles an hour, it looks to be that my coefficient of drag is about 0.52. So I'm going to choose that number because this kind of average coefficient of drag over the entire flight. So I'll click OK. And I'm going to go to the CD Override tab. And I'm going to say, I'm going to uncheck this box over here at the left that says Calculate CD at the simulation time. So now I'm going to say, don't calculate the CD. This is what I want. I don't want it to calculate the CD. I wanted to use a specific value. And the value I wanted to use is 0.72. So I have to uncheck this. And this forces RockSim to say, we're going to use a static coefficient of drag. And I'm going to just rerun the simulation again. So I'll just click the long. And now my altitude has changed again. Because now we have a fixed coefficient of drag. And if I launch it again, I should get the exact same number. So now we're narrowing things down. Okay, so now we've narrowed down the coefficient of drag. We also need to narrow down the mass of the rocket, or the location of that center of mass. We don't want things shifting around, because when the rocket is burning, the back end is getting lighter and lighter and lighter, and the center of gravity is shifting forward towards the nose of the rocket. And what we need it to do is to stay in one particular spot. Because the center of mass is shifting forward, the moment of inertia of the rocket is also changing. And so if the rocket starts wobbling, and the moment of inertia is changing, the trajectory is going to change. So we need to fix the mass of the rocket at a specific point so that the moment of inertia of our rocket doesn't change throughout the entire flight. So now you need to go here to this mass override tab, like you did the coefficient of drag override tab. And when you go here, now this time, instead of unchecking the box, we need to check the box. This time we're going to say, we're going to force it to use the values below. Now we need to measure the mass of the rocket. And since I have the actual rocket here, I'm actually going to weigh it. Now this rocket doesn't contain a streamer or a shock cord, as you can see. And it also doesn't contain an altimeter. So when you weigh everything, everything has to be in the rocket. So I'm going to put my altimeter on there. And I'm just going to estimate that my streamer weighs 3 grams. I don't know what it weighs because I don't have one sitting here, but 3 grams. So if I look on my scale right now, it's at 10.2 grams. I'm going to add 3 more grams for my streamer. So now I'm at 13.2 grams. So I'm going to put that here for the sustainer mass. Now we also need to know where the center of gravity is on this rocket. And this is empty. So I got to take my, if you can see on the little screen here, I'm taking my altimeter and I'm putting it inside along with the battery. Now the streamer is probably going to be there, but if I balance this rocket, it seems to be balancing right there. And if I put the streamer right there, it's probably going to balance somewhere pretty close to there. So I'm balancing right there. I'm going to take my ruler and I'm going to measure where that balance point is. And I'm at about 5 inches. So I'm 5 inches from the tip of the nose. So I'm going to hit this at 5 inches, hit enter. And it's not quite in the right location. Well, one, I'm sure, okay, so if you look on the screen, it's not at 5 inches. And the reason is we're showing the booster stage. So let's come over here to change the visible stage selection button and change that to just show the upper stage. Now the center of gravity shifted back, but it's still, now it's further back than what it actually is on the rocket. And the reason for that is because we have a rocket motor in there. So I need to unload the rocket motor. So I go to prepare for launch, highlight the body tube and say clear all or clear selected, and it will clear out the rocket engine. And I click OK. Now, when I go back to my screen, my center of gravity is in the right spot. Okay, so now we're all set. Now, I want to reload my motor back in. So I'm going to go back here, choose my engine, A34. So the motor is now loaded back in. I'm going to check over my simulation events, deploy at maximum ejection delay. I have a starting state. It's launched straight up at 36 inches. Under launch conditions, I have a 8-mile-an-hour wind, and I'm launching at an altitude of 700 feet. I'm going to click the flight profile button because I want to actually see what this launch looks like. And in our last video, I always said, always look at profile because you want to see what's really going on with your flight. So down here on the screen, we have the rocket sitting. It's straight up, and if I click the little launch button, it will start the animation and the rocket takes off. As you can see, it's going up, going up, going up. Oh, and it pops out the streamer. I don't know if you caught what I saw looking at this. I noticed 2 things that are going to affect our altitude. Okay, so let me stop this, and I want to go back in the animation. Well, first back to the very beginning. First of all, as it's coming off the launch pad, it's wiggling around a little bit. And that's because when there's wind, the wind is pushing on the side of the rocket and it's wiggling it around, and until the rocket hits enough speed to dampen out all those little wiggles. So actually, you know, this, what you're seeing is very realistic. And you go out to a launch range, this is what you're going to see. As the rocket comes off the pad, it's going to wiggle around a little bit until it finds its speed to punch through those little oscillations. And now it's starting to go straight. But the thing to notice here is this smoke column, it's not straight up. It's tilted off to the side, so our rocket is actually weathercocking into the wind. We talked about this in the last presentation. This is normal, but you have to fly with the conditions that you're flying in. So when you do optimum mass, you have to know what the conditions are, and we'll zero out the wind in a little bit to see how it changed. Okay, so now the next thing I noticed, the rocket's going up, it's still going up, going up, going up, it's slowing down, starting to arc over at the top. But you can see as the streamer came out, it all of a sudden flipped around. And now my tail is going up. So the rocket is going so fast going up that it has a lot of momentum. The streamer comes out, it whips around to the bottom because the rocket has still momentum going upwards. So what this tells me is my delay is too short. I need to fly this rocket with a longer delay to get to that peak altitude. So again, this is another variable that to throw in that optimum mass equation. So how do I change the delay? So I have back to the launch preparation screen, and I can do it from right here. My engine ejection delay. If I click on the drop-down menu, it'll show me what delays are available. Unfortunately, in real life, Estes only offers a 4-second delay. For this rocket, it's not enough. We need a longer delay. So, what do we do? Well, in real life, I can't change it. It's one of the limitations of this launch. But in RockSim, I can change it. I can select custom. So if I choose a custom delay, now I can type in any value I want. So I'm just going to go longer than 4 seconds. Oops, I'm clicking the wrong button. Let's make it 9 seconds and see what happens. So I'll use 9 seconds. And I'm going to rerun the simulation. When I launch it, if you look over here on the side, even before I play the animation, I can see that my altitude didn't change much, but by going to a longer delay, I did eke out a little bit of extra altitude. Let's see, I have an optimum delay of 4.45 seconds. So at 9, I expect the rocket to go over the top and start coming back down when the streamer comes out. And let's just run that simulation for about 10 seconds and see what actually happens. The rocket goes up, hits the top, starts coming down, and a streamer comes out. Comes way over the top. And the question is this delay too long? Well, maybe is the answer. When you're flying altitude, you expect your rocket to go really, really high. And at that point, it's really, really hard to see. So imagine you're looking down from the ground straight up. All you see is the bottom of the rocket, just a little tiny dot. And this rocket is at 500 feet, and you're looking for a little dot in the sky. Well, maybe could you see that little dot better if the rocket was lower? So when this streamer comes out, let me back up the simulation. The streamer is popping out right here, and at this altitude, we're almost 300 feet. So 585 feet up in the air or 300 feet up in the air. Which gives you a better chance of seeing your rocket? Obviously, if the rocket is lower, it's easier to see. So when we fly altitude rockets in competition, this is actually a very desirable launch situation where you have an extremely long delay. It comes over the top, it's lower in the sky when the parachute comes out, so it's easier to see. Remember, we got a little altimeter inside of there. We don't know what the actual altimeter is going to read until we get the rocket back. If you lose your rocket because you can't find it, you lose the event. So it's very, very important to get your rocket back so you get your altimeter back. And these little altimeters aren't cheap to begin with. But then you lose an altimeter and lose the contest because you lost your rocket. That's like pouring salt on the wound. We want to get that rocket back. So we actually do want it to go over the top and be coming down. But at the same time, we also have to make sure it comes down in one piece. If you shred your streamer, if it's coming down so fast, it's coming down at Mach 1, and your streamer comes out, what's going to happen to that streamer? It's just going to, and you're going to lose your streamer. And that will also disqualify you in an altitude contest because you have to be safe. If your rocket comes down unsafe, you're disqualified. So now we got the rocket screaming back down. So we need to actually figure out what speed this rocket is as it's deploying its streamer. We can get that in two places in RockSim. We can actually get it on this screen here if we click on the details button, and it will tell us our velocity. And right now it's saying our velocity is 43.4 miles per hour, but that's actually with the streamer deployed. Once the streamer is out, we got to go, what's the velocity right before it comes out? So I'm backing up the simulation here, and at this point the streamer is not out, as we can see, and we can look here at the velocity, and our velocity is actually not too bad. It's at 70.6 miles per hour. Okay, so let's cancel out of there. You can also get that velocity right here on the summary screen at velocity at deployment at 70 miles per hour. Normally, I like to keep my velocity of deployment less than 50 miles per hour if it's 50 miles per hour, either parachute or streamer, because at that point I know that the parachute can probably survive. So if I was choosing this trajectory, I would look at this number to say, am I under 50 miles per hour? Here it says no. So I need to slow the rocket down so I'm not shredding off my streamer. So I would actually choose a shorter delay, but still longer than that 4-second delay to get a slower speed. But I'm getting way off track. So I want to go back to optimum mass now. So now we have everything dialed in on optimum mass. Again, what we need to dial in is the center of gravity, location, and the mass, and also a static coefficient of drag, and a wind speed that's either constant or zero wind speed. So now let's go back up to simulation, and we're going to go predict optimal mass again, and just click start the simulations. It's running the simulations again. You can see it's real quick. It figured out our optimal mass is now 8.56 grams. Let's look at the graph. Oh, my graph is still not looking good. Something is wrong. Let's cancel out of that. Let's run it one more time. Nope, still the same. There was a old bug a long time ago that created this type of situation. I'm just seeing if it was still in this version, but it's something is my setup is wrong here somewhere. Uncheck my simulation. Sustainers, I need to ignore all these. That's okay. Use these values for the simulations. Oh, I hate it when things go wrong when I'm live. Let's go back here to starting state, launch conditions, custom speed range. That's okay. Let's rerun a simulation. Let's choose a different a different delay. I don't know how that could change things. 585.2421, so that's the same. I'm looking at this number right here, comparing it to 2 simulations ago, and that has changed. Or I mean, that's exactly the same number. This simulation number 14 versus number 12 over here on the side. And I launch it, it's gone up. Okay, that simulation looks good. And optimal mass. Start the simulations again. 8.7, that's pretty close to what it was. Plot graph, it's still the same. Okay. I want to do that, and let's make this screen a little bit bigger so you can see these here. So let's make my starting mass 3 grams, my ending mass 20 grams, and I'll increase every half a gram. So we'll probably run a bunch of simulations. I should be done by now. Let's plot it, see what we got. Whoa, yeah, that's crazy. Something is varying in my simulation, which is what I'm seeing here. Now I have to figure out what is varying. I'm looking over here in our comments. I think someone asked last week about motor clusters. Would you mind taking the time during one of these events to talking about cluster? I'm looking over here on Facebook. See if, because sometimes you people out there are smarter than me, and you can see where I screwed up. Mass override. I did this last night and it worked perfectly. So this is why I'm trying to figure out what's going on here. What is varying that's causing things to go crazy? I'm going to take the booster for right now. I'm going to delete it. So I'm going to go to Design Attributes and delete my booster by just changing it to a single stage rocket. And say yes. And that simulation, see if that changed things. This is how you troubleshoot things as we go along. Please select a simulation. So I need to select a simulation. Rerun all, oops, I don't want to rerun all simulations. That was dumb. I want to check that one and predict optimal mass. Start the simulation. This time I'm going to do this. 8.4. It changed a little bit. Yeah, see, I'm getting a crazy variance right here. It shouldn't be. It should be a nice smooth curve, like that very first time that we did this. This is why optimal mass is challenging. What could be varying in this simulation? Deploy a maximum ejection delay. Let's deploy at Apogee. Simulation, when the rocket reaches the ground, starting state 36 inches straight up. Launch conditions. Let's change this. Let's change it to 0 miles per hour. No thermals. No competition. So flight profile this time. This time I expect the rocket to go perfectly straight up and come straight back down. All right. And you can see my altitude did go up a little bit because we are going straight up and there's no wind causing it to weathercock. So that's expected. It seems like it's my coefficient of drag that's varying. So let's go Coefficient of drag versus velocity. Now this one should be a flat line, and it is a flat line. So that is good. Predict optimal mass. Start the simulations. So the first thing I notice right here is the optimal mass changed again. So when the rocket, when there was no wind, the optimal mass dropped. So what we're looking for here is kind of like design philosophy rules. So if you're launching in windy conditions, you can tolerate a little bit more mass than if it was calm. Plotting the graph. I'm getting a better curve here. It's still showing my optimal mass right here. I did this exactly last night. And I had a really beautiful chart. This chart is not bad. It's got a nice smooth curve here. It just doesn't like the altitude when it's under 6 grams. Let's see what happens. Let's go here to our mass override, and let's change our sustainer mass to 5 grams. And that's all we're changing. And let's rerun this simulation and see what happens. I'm getting exactly the same altitude. Load engines. Maybe that. I didn't do it. Oh, I didn't do what the engine loaded. Predict optimal mass. Start. Plot graph. Oh, that's even worse. So something's going on when the engine is loaded. I'm trying to think. Anybody out there that's smarter than me, seeing what I'm doing wrong? 590. I got a lower mass, and my altitude is still going. Oh, I think I know why. My delay is too short. So let's change the delay again. Let's go to a custom delay. Let's go 9 seconds. Flight profile. Just see what it looks like. Again, it goes straight up, comes straight down. That's good. This time it went higher because I had a longer delay. Predict optimal mass. Start the simulation. Plot the graph. Still got a crappy graph. It doesn't like anything under an optimal mass of around, in this case, 17 grams. Wow. Current mass is 5, peak altitude. There's something going on here. And we're doing this live. And I am sure it's a setup that I'm screwing up. So I'm going to have to dig into this and figure out what's going on. You can also send me a comment if you have a message. Send it to me. Like I said, sometimes there's a lot smarter people out there than me. But this is the general gist of optimal mass. And again, I said from at the beginning, this is listed in our newsletters, and the issues are number 84 and number 200, how to set it up. But I don't have this set up quite right. I'm missing something. And I'm going to have to figure it out, and I'll talk about that the next time. But we're about an hour right now, so I want to conclude this video because I don't want to take up all of your time. So I'll go back here to the profile view. So the key with optimal mass is it is the high end of complexity, and there's things that are far, far more important than optimal mass. One is reliability. If your rocket is not reliable, it doesn't matter what your optimal mass is. Number two, you got to get your rocket back. So what can you do to make sure you get your rocket back so you can prove the altitude? One of the things that I always do is the color. You can see when I do an altitude rocket, I paint it fluorescent colors because fluorescent is definitely not a natural color out on a launch field. You can see a fluorescent red rocket or a yellow rocket laying on the ground far easier than you could see a brown one if it's unpainted. So that's why I always paint my rockets a fluorescent color, just to be able to get it back. Also, when you put your streamer in there, choose a bright color streamer. Again, you want to be able to see your rocket. So you have, reliability is important. Next is coefficient of drag. When you run your optimal mass calculations, that coefficient of drag plays a far greater role in the performance of the rocket than the optimal mass. So you don't have to worry about optimal mass until you optimize for coefficient of drag. So you want to make sure everything is as smooth as possible. Making your airfoils, making sure that you actually sand an airfoil into your fins. The airfoil is that cross section of the fin. So a regular sheet of balsa wood has a square front end and a square back end. You want to at least round off that front and back end so you make it more aerodynamic and the coefficient of drag comes down. That gives you more working room for your optimal mass. So that's very important as well. Optimal mass in RockSim, it's only looking at, which we didn't get into, was only looking at the sustainer. Once you put a booster on it, it still only looks at the sustainer. But if you have a booster attached, it's going to affect your altitude. So now you have to figure out what is the optimal mass of a booster. And I'll tell you right now, the optimal mass of a booster is 0 grams. So if you're flying a two-stage rocket and you're trying to figure out optimal mass, make sure you make your booster as light as possible. And the people that agonize over that are competitors like Steve. I'll show you some rockets. This is a two-stage rocket similar to what Steve is flying for competition. And we have the sustainer, which is small, and you have a big booster. And why is it a big booster? It's because the rules in his particular event say you have to have a booster, or the rocket, the overall shape of the rocket has to be 500 millimeters tall, and half of the length must be 40 millimeters in diameter. So we have to have a section of the rocket that's 40 millimeters in diameter. So where do we want to put that 40 millimeters section? Do we want to put it at the top or at the bottom? Well, when you fly a stage rocket, you can get rid of this real quick. Now all of a sudden your diameter goes way down. And so your rocket can go a lot higher by dropping this as quickly as possible. But this has to be as light as possible. Now this particular booster stage, I lost a fin, but I weighed it previously. It weighs about 10 grams. That's less than the weight of this rocket, with its booster. And the reason is everything is super, super ultra lightweight. We went to a fiberglass tube, and it's not that fiberglass is lightweight, but with fiberglass you can make the wall thickness wafer thin. Glass is actually very heavy. I don't know if you've ever picked up a pane of glass, but it's heavy. But if you can make it wafer thin, it can be really light. You can even go lighter than that. You can make carbon fiber. Now these are carbon fiber and epoxy fins. I could actually probably make them lighter by going to balsa wood. The reason I use carbon fiber on these is that it's thinner than a balsa for the same strength. So I can kind of reduce my drag just by going to a thinner material. I haven't even worried about optimal mass yet, but you can see of all the design considerations that I'm doing even before I'm going into RockSim trying to figure out optimal mass. So in the future, like how can I make it even lighter? So one of the things that I'm experimenting with is carbon fiber. Same exact shape, same size, but this one is lighter. This one weighs 7 grams. This one is 10 grams. So I'm 30% lighter by going to carbon fiber. This is just a prototype, and I haven't actually flown it to actually see if it will actually survive. Again, reliability. If it's not reliable, and if it shreds on the way up because it's too thin and too weak, you know, you're losing the battle right there. So it's got to be reliable. So this is why I don't talk about optimum mass very much, because it's the last thing you want to worry about until you figure out how to get that coefficient of drag down, how to get your mass down, so then you can start building up. So say I got the mass of this rocket down below optimum mass. You know, this is my sustainer, so this is the important part. Let's say the sustainer had to be 5 grams empty weight without the rocket motor. And when I build it, I'm at 3 grams. So basically I got 2 grams to play with. Where am I going to use that 2 grams? Two things to think about here. Where on the rocket it will actually go. And I want to put it at a location probably at that center of pressure, because if the center of pressure location is going to determine how the trajectory of the rocket. If you move the center of pressure back, or if you move your center of mass forward, I got that wrong. If you move your center, where do I want that center of mass? If you move the center of mass forward, the rocket is going to weathercock more into the wind, and I'm going to lose altitude. I want a rocket going straight up. So I want to put that center of mass further back, closer to that center. I want it to be right on that hairy edge, but still be reliable, nice and straight. But then the other thing is, what kind of mass am I going to put in the rocket? In this case, the mass I want to put into the rocket is mass that will improve reliability or the ability to find the rocket. Remember, we got to get the rocket back. So how can I find the rocket easier? How about a bigger streamer? Is a bigger streamer going to be easier to find than a smaller one? Maybe I want to paint the rocket. If I can paint the rocket, maybe I can make it smoother. Paint is going to add weight, but will it make the rocket smoother? So now my center of, or my coefficient of drag is also coming down. So there's a lot of these design considerations to play with before you get to optimal mass. But I will figure this out, what I'm doing wrong, and I will show it in the next episode. And I want to conclude because now we're like way over time here. We're 8 minutes long. So you're watching the RockSim Live, where we're trying to train you about how to use RockSim. And at the same time, you're getting a lesson in aerodynamics and structural analysis and rocketry in general. So I am training you to be a rocket scientist, which is really cool. You know, because if it was just about RockSim, this would be boring. RockSim is just a tool to help us to be better modelers. And that's where its real value comes in. And I can't emphasize enough what an important tool RockSim has been for me. I'm always learning new things about rockets just by running simulations and just varying things like we've been doing here in this episode. Yeah, so if you don't have RockSim, we have a free trial. You're welcome to download that and play with it for 30 days. I think you're going to love it. It's a really cool program. I think it's far more valuable than what we actually charge. Anything that can make you a better modeler, that can make you save money by finding your rockets, so you're not losing rockets, your rockets aren't shredding, you know, they're not going unstable. That's saving you money right there. And you can run all kinds of simulations even before you actually go out and build your rocket. So now you're saving money picking rocket engines and picking your launch conditions. So it's all about saving you money, making you a better modeler. So that's RockSim. One of the things that I wanted to do in this episode, I wanted to do a poll. I wanted to ask you a specific question. I didn't have time for that, so I'll do that the next time. So we're doing these every Friday at 10 a.m. Mountain Time Zone. So that's 12 noon Eastern or 9 a.m. on the West Coast. And if you're in different parts of the world, you can 10 a.m. Mountain Time. Google, if you go to Google, you can just do the conversion. What is 10 a.m. Mountain Time in my time zone? And it will tell you what time these are actually showing up live. If you have a comment, you can leave it here, or you can put it on our website. We do look at the comments. I showed you at the beginning how to navigate our website to leave those here. So my name again is Tim Van Milligan. Thanks for coming to this RockSim Live, and we'll see you next week. And I will try to have this figured out by then, because this is very embarrassing. I know it's not a problem in RockSim. It's my problem. I don't have something set up right. So I can now quick the end simulation.